Okay. Oh, so far, everything looks like it's working. All right, so today we are going to start section 4.3, which covers the maxima and minima of a graph, or mainly of a graph. Okay, so what if we let f of x represent a defined, move that mouse out of the way, there we go, represent a defined function over a specific interval. So let f of x be defined on an interval I, which is just from x equals a to x equals b. So sometimes you'll see from x equals a to x equals b. Sometimes you'll see the interval I. Same thing, just different notation. Okay. Then we know that f of c is what is called the absolute minimum of that function f of x if f of c is less than or equal to f of x for every x in the interval. And clean up that e a little. There we go. Whole page on there. Here we go. Okay, and we know that f of c is what is called the absolute maximum of our function f of x if f of c is greater than or equal to f of x for every x in the interval. Okay, so let's see what that means visually. Okay, so let's say if we have our x and y axis, and let's say we have some graph that looks like this. And make this a little bit longer. There we go. Okay, so we'll highlight all of the low and high points in the graph. Okay, so we're just looking at the interval from A to B. So this graph could keep on going in both directions. We're not really worried about that. We're just looking between A and B. So if we look at the highest point, or I guess you could say the greatest y value or f of x value on this graph in that interval, then this point here would be your absolute maximum. Okay, so in that interval, it doesn't get any higher than that point there. And if we look at all of the low points, we can see here that this is the lowest point out of all of them. So this is your absolute minimum. Okay, but these can be a little bit tricky, only because, let's say if we have that same graph or a similar graph, I won't say the same one. Okay, but let's say here we have an open circle. And we'll put a closed circle right there. And we'll put an open circle here. And we have the same interval from A to B. Okay, so again, if we highlight all the high and low points on this graph, and let me make that open circle a little bit bigger, just because to make sure it's viewed as an open circle. Okay, so let's say this interval was from -1 to 5. And just temporarily, I'm just going to erase this b and make, actually, I can just put b is equal to 5. So I can keep the b there, just for an example. Okay, so we can see the highest point on this graph is right here at 5, but it can't equal 5, which is why we have the open circle. The only problem with that is we can't say that's an absolute maximum because it can't equal 5, but it can equal 4.9, 4.99, 4.999, you can keep getting closer and closer and closer. So there's no absolute maximum because you can always get a little bit closer. So with this one, even though this is the highest point, it's no absolute maximum. Now, all these points here, those are your local maximums. That just means in this area around that low point, that's the lowest. In this area around that high point, that's the highest. In this area just around here, that's the lowest. So it's just around those high and low points. Those are your local or relative maximum or minimum. But overall, over the whole thing, those are your absolutes. Now, we still have an absolute minimum. So you can have no absolute maximum and an absolute minimum, or you can have no absolute minimum and an absolute maximum. You can have neither. It all depends on those open and closed circles. And if those open and closed circles are near the highest points or the lowest points on the graph. Okay, so if we draw a similar graph one more time, again from A to B, draw closed circles. We'll draw this one as similar as we can to that one. Again, we'll make this a little bit lower. I want that to be lower than this one. Uh-oh. There we go. But at that low point, we're going to make that an open circle. And actually right here, we'll make this a closed circle, just because. Okay, so on this one, we have an absolute maximum because this is the highest point in this interval, and it actually equals that value. So we have an absolute maximum. But the lowest point on that graph is not absolute. Again, because of that open circle, let's say this is 1, just for example. We know it can't equal 1, but it can equal 1.1, 1.01, 1.000, and closer and closer and closer, an almost infinite number of times. So there's no absolute minimum. So there can be a combination of any of those, just depending on the graph. There can be both the absolute maximum and minimum. It could be neither one. It could be one, but not the other. Or if you had 2 points that were at the same height, let's say this little portion of it was equal to that absolute maximum. You could have more than one. All right. So any questions on that so far? All right. So now we're going to take this and we're going to look at what is called the extreme value theorem. Or most of the time you'll see EVT as a shortcut. Okay, so let's say if our function f, it could be f of x, f of t, whatever it is a continuous function on some interval I, which is from x equals a to x equals b, if the independent variable is x. Oh, actually, this should be closed because it does include the endpoints. And differentiable on that same interval, but it doesn't have to include the endpoints. Then we know that f of x has an absolute minimum and an absolute maximum. So all that means is that if you have a graph, and we'll just put a little just to visualize it, we don't need the whole thing. If between A and B, the function is continuous and differentiable, which means there are no openings anywhere. You just have one continuous graph. Then that means you have to have an absolute maximum and minimum somewhere in there. Okay. So if you had one that was not differentiable, that means the limit from the left and the limit from the right wouldn't be the same at each and every point, which means it wouldn't be continuous. Okay. So let's say, for example, if we want to just consider the function, let's say f of x is equal to x squared plus 4x minus 1 to the 3/2 power minus 9 over the interval from x equals 3 to x equals 8. Clean up that 3 a little bit. You want to know, does the extreme value theorem guarantee the existence of an absolute minimum and maximum? Absolute minimum and absolute maximum. Excuse me. Okay. Now with this one, you just have to remember a rule about functions and continuity that, so let's say if f of x, g of x, and h of x are all continuous, then we know that if you add them together, f of x plus g of x plus h of x is also continuous. Okay, so adding continuous functions will give you a continuous function. If you add differentiable functions, that will give you a differentiable function. Okay, so what we have to do is we have to see for f of x is equal to x squared plus 4x minus 1 to the 3/2 power minus 9. We want to see if each and every one of those terms are continuous on that interval. Okay, well, let's look at x squared. Well, if we plug in any value between 3 and 8, we'll get a real number. Well, it's continuous. There are no undefined values for x squared. So we know that this is defined and continuous. over that interval. Okay, and let's look at -9. Well, it's a constant, so it's defined no matter what interval you have. So this is defined and continuous. Okay. Now this middle term, this one, just looking at it, you can't tell. So you have to kind of figure out whether or not that one's defined and continuous. Okay. So if we take 4x minus 1 to the 3/2 power, we can rewrite that as 4x minus 1 to the 1/2 power, and that raised to the 3rd power. Because we multiply those two, we'll just get our 3/2. Okay. So we know anything to the 1/2 power, that's just the square root. So we could say that this is just the square root of 4x minus 1 cubed. Okay, so we know that this square root will be defined as long as the radicand 4x minus 1 is greater than or equal to 0. It's the only stipulation. If it goes less than 0, then you're no longer dealing with real numbers, and it won't be defined there. So we know that 4x minus 1 has to be greater than or equal to 0. So if we add 1 to both sides and divide both sides by 4, that means that x has to be greater than or equal to 1/4. And kind of highlight that a little bit. Okay, so we know that it's continuous, defined, and will result in a real number for this interval. Which is pretty much from 1/4 to infinity. Okay, so just to visualize, we have our x is greater than or equal to 1/4. Okay, so we have 1/4. So we know everything greater than that is defined. Defined and continuous. Okay. So if we look at our interval from 3 to 8, well, this is 1/4. 3 could be somewhere over here, and 8 could be somewhere over here, which actually falls in that defined interval. So this middle term is actually defined and continuous. So we know that because all 3 terms are defined and continuous, that the entire thing is defined and continuous. Okay, so we know that this function is guaranteed to have an absolute minimum and maximum. I'll just put min and max by the extreme value theorem. All right, any questions on that one? Okay. Now, if the interval would have been from 0 to 8, because 0 falls outside of that interval that's defined for, then it wouldn't be guaranteed 1. So because both of your endpoints in the entire interval does fall within that range, then it's guaranteed. All right, anyone still writing? All right. Okay, so let's say, for example, if for f of x is equal to 6 divided by the square root of x squared minus 16 over the interval from 3 to 5. Did I grab it? Yep, I did. Oh, well. Actually, let me rewrite this on another sheet of paper. Somehow, some other notes got mixed in with my clean paper, saying it like I didn't do it. Okay, so for f of x is equal to 6 divided by the square root of x squared minus 16 over the interval from 3 to 5. Does the extreme value theorem guarantee the existence of an absolute minimum and absolute maximum on this interval? Be a little more specific. On this interval. There we go. Okay. So we know that because of this denominator, the square root of x squared minus 16 has to be greater than 0. It can't be greater than or equal to, only because you now have that in the denominator. So if you made it equal to 0, it will be undefined. So we know that this square root has to be greater than 0 for this to be defined. Which means that the radicand x squared minus 16 has to be greater than 0. So if we add 16 to both sides, those two cancel each other out. We know that x squared has to be greater than 16. So we know that x has to be greater than 4, or x has to be less than negative 4. And that's because if you take, let's say you have 4, let's say you have negative 4 here and 4 there. So let's say you have 5, 6, and negative 5, negative 6. if you plug in any value, that should be a parenthesis since it's just greater than. If you plug in any value larger than 4, your x is greater than 4, it'll make this true. So 4 squared wouldn't make it true because 4 squared is equal to 16 and it's just greater than. But if you put in 5 squared, 25 is greater than 16, 36 is greater than 16, all of those will work. Now, if you plug in any value less than -4, say you plug in -5, -5 squared is positive 25, which would make it true. -6 squared is positive 36, which would make this true. You can't pick any number between there because they wouldn't work. So any number greater than 4 or less than -4 would make this true. Okay, so this is our defined and continuous interval, or intervals, since it's more than one. Okay, so let's get those two values. Oh, that should be infinity. And this is negative infinity. Okay, let's say our 0 is here. So we'll put 4, 5, 6 here. So we know every value greater than 4 would make this defined. And if we put our -4, -5, -6, every value less than -4 would also make this defined. But if we look at our interval from 3 to 5, and we're looking for from 3 to 5. Okay. Now it's defined on this part, but it wouldn't be defined here. Let me clean up this 5 a little bit. Here we go. Okay, so because of this missing defined portion of it, we know it's not defined on that interval. So if it's not defined on that interval, then it's not defined from 3 to 5, just for a part of it. So because of that, we know that it is not continuous and defined. So f of x is not continuous throughout the entire interval from 3 to 5. Throughout the interval from 3 to 5. So there's no guarantee that the absolute maximum and minimum exists. So the existence of an absolute minimum and maximum is not guaranteed. By the extreme value theorem. All right. Any questions on that one? All right, anyone still writing? Oh, still writing. Okay. Okay, so let's say, for example, we have for f of x is equal to 2 times e to the power of 7 divided by 2x minus 6 over the interval from 3 to 7. Does the extreme value theorem, move that over a little bit, guarantee an absolute minimum and absolute maximum? Okay, so let's look at our function f of x equals 2 times e to the power of 7 divided by 2x minus 6. Okay. So this would be defined everywhere except wherever that denominator is equal to 0. So we know that 2x minus 6 cannot equal 0. That's the only spot where it will be undefined. So if we add 6 to both sides, we have 2x cannot equal 6, and divide both sides by 2, we have x cannot equal 3. So you're good everywhere except where x is equal to 3. Okay, so that means we draw our number line. As long as x does not equal 3, and I'll just put an open circle there for 3, you're okay. So x can equal any value to the right and any value to the left. And you're okay. Now, the only problem is this interval from 3 to 7 includes 3 and it includes 7. So it includes 7 and it has to include 3. Okay, so the fact that this is an open circle shows that it doesn't include 3. Okay, so we can see here that right at that point, because it's not from 3 to 7, so we know the point x equals 3 is in the interval but not defined or continuous. We're more concerned about continuity since that'll give us whether or not it's defined. So we know the extreme value theorem does not guarantee the existence of an absolute minimum or maximum. Oops. Guarantee an absolute minimum or absolute maximum. All right. Any questions on that one? All right. Oh, anyone's still writing? Oops, still writing. Oh, anyone else? Looks like everyone's done. Okay, so with one more example, then we'll move on. Well, still in this section, but the next topic. Okay, so does the extreme value theorem guarantee guarantee the existence of an absolute minimum and maximum for f of x is equal to cosine of x divided by sine of x over the interval pi over 4 to 3 pi over 4. Okay, so let's look at our function f of x equals cosine of x divided by sine of x. Okay, so even though cosine and sine are both continuous, continuity is not guaranteed when you have the division of two continuous functions. So you can add them, you can subtract them, you can multiply them, you'll get a continuous function. But if you divide them, it's not really guaranteed. Okay, so we know in this case, well, in every case, the denominator can't equal 0, but in this case, that means that sine of x cannot equal 0. Okay, so let's take a look at the values that will make sine of x equal 0. So that means not sine of x, but x can't equal 0 because sine of 0 is 0. It can't equal positive or negative pi because both of those would give you 0. Positive or negative 2 pi. Positive or negative 3 pi. Or any integer n times pi. All of those will give you a denominator of 0. So let's draw out our number line. from negative infinity to infinity. And since pi over 4 and 3 pi over 4 are both positive, we'll just worry about the positive values. Okay, so we have 0. We have pi, 2 pi, and we'll stop at 3 pi. So we know that x can equal pi. So we'll draw a little vertical dotted line showing that's off limits. It can equal 0. So we'll draw a little vertical dotted line through there. It can't equal 2 pi. And it can't equal 3 pi. So those are the undefined values just on our little graph. But anywhere between there is perfectly fine. It's defined everywhere. Okay. So if it's defined between 0 and pi, but just not at those endpoints, well, pi over 4 is somewhere around here. And 3 pi over 4 is less than pi, so it's somewhere over here. So let me make the bracket a little bit closer to that point. Here we go. So that's our entire interval right here. Which means as long as it's not pi or 0 or somewhere crossing those two, or either one of those, it's defined on that whole interval. Because it's right there in that defined area. So we know that f of x equals cosine of x divided by sine of x is defined and continuous. Over the interval from pi over 4 to 3 pi over 4. So an absolute maximum and absolute minimum are guaranteed by the extreme value theorem. All right. Any questions on that one? Does that kind of make sense? All right. Anyone still writing? All right. Okay. Now let's look at some topics that we should already know. Okay. So what if we have a quadratic function, or the graph of a quadratic function, and we'll call this just f of x. Okay, so we know that whenever the part of a graph is increasing, the slope of the tangent line, or your f prime of x, is going to be positive. Just greater than 0. This way. Actually, let me move that down just a little bit so it won't be in the way of the rest of my writing. So f prime of x is greater than 0. And we know whenever the graph is decreasing, the slope of the tangent line is decreasing. or we know that f prime of x is negative or less than 0. And we know whenever the slope of the tangent line is horizontal, that's where your f prime of x is equal to 0, or your slope of the tangent line is 0. Remember, a constant slope is just horizontal. Same thing here, constant slope of the tangent line, horizontal. Okay. Now on this graph, where your f prime of x is equal to 0, that's your absolute maximum. That's the highest point on the graph in any interval there, as long as that interval includes that high point. Okay. Now, what if we have a graph, same graph, but we flipped it around? Okay. Again, we know it's decreasing when the slope of the tangent line, or move that up in a f prime of x is less than 0. We know it's decreasing. Same thing with this interval. We know the graph is increasing if f prime of x is greater than 0. And we know it's a constant slope when f prime of x, or your slope, is equal to 0. Okay, so we can see here at this point where your f prime of x is equal to 0, that's your absolute minimum. That's the lowest point on the graph. Okay. Now those values are called your critical points. So the critical point is where f prime of x is equal to 0 on an open interval from a to b, or f prime of x is undefined. Now for this graph, let's say if we're looking at I'll do the positive one first. So let's say if we have our graph that looks like this. Okay, so you can see here that the slope goes from negative to positive. It's steadily increasing. You can kind of picture it and find something kind of thin that I could use to represent the slope. Okay, so I'll use this paper clip. Okay, so if we look at the slope of the tangent line, at any point it would be kind of like this. But as you go to the right, you can see that slope slowly increase. So it may start here at like -2, but as you go to the right, it slowly increases to where you have a slope that equals 0, which is at the lowest point. And then it just slowly keeps going up and up and up as you go to the right. Now, if that slope of the tangent line steadily increases, then the rate of change of the tangent line, or the derivative of the first derivative, would have to be positive. So we know that the positive second derivative, or the second derivative at some point, we'll call this point C, that will be your minimum. So we know that is called concave up. It means the graph is concave up. At x equals c. And I'll just put that on a little number line there. Okay. So that means your minimum, or your absolute minimum, will be at f of c. But what if we have that same graph, but we flipped it around, and at the point x equals c, that's the top of the vertex, or the peak of the vertex. Okay. Now in this case, we can see that our slope would start off positive. So it starts off positive, and it's steadily decreasing, because as it goes to the right, it's now moving, decreasing to where it's eventually 0, and from 0 it just becomes negative. It just keeps decreasing. So that means the rate of change of the tangent line, or the derivative of the first derivative, is negative because it's decreasing. So that means if at that point C, that second derivative is less than 0, that means the graph is concave down. At x is equal to c. Which means that point will be your maximum. At f of c. Let me clean that m up a little. Now, the one way I used to always remember this, because we weren't allowed to use notes or anything on the test, is with concave up. Make that a little bit longer. If you see the C-U-P, I just thought of cup. And it kind of looks like a cup. That's how I remembered it. Anyone still writing? All right. So let's say, for example, we wanted to find the critical points for f of x is equal to 4/5 times x to the 5/2 power minus 4x to the 3/2 power plus 2. Okay, so for this one, you want to remember that your critical point is where your derivative is equal to 0 or your derivative is undefined on an open interval from A to B. Okay, so if we take our f of x equals 4/5 x to the 5/2 power minus 4x to the 3/2 plus 2, then our f prime of x is going to equal 4/5 times the derivative of x to the 5/2 power. So we bring down the 5/2 and we subtract 1 from it. So 5/2 minus 1. Minus 4 times the derivative of x to the 3/2 power. So we take that derivative, we bring down the 3/2, and we subtract 1 from the exponent. Plus the derivative of 2, which is just 0, but I'll write it out anyway, just to cross it out. Okay, so if we go ahead and multiply these two together, just to simplify it, we know f prime of x is equal to, the two 5s cancel each other out. So we have 4 divided by 2, which is just 2. So 2 times x to the 5/2 minus 1. So we have 5/2 minus 2/2 is 3/2. Minus, and we can go ahead and multiply these two together just to simplify it. So 4 times 3/2 is 12/2, which is just 6. So 6 times x to the 3/2 minus 2/2 is just 1/2. That's to the 1/2 power. Okay. Now notice here, I'll write this on the side. So you want to notice for this one, if you take that x to the 3/2 power, you can rewrite that as x to the 1/2 power cubed, because 3 times 1/2 is 3/2. So So that just means you have the square root of x to the third power. Same thing here. That x to the 1/2, that's just the square root of x. So we know for both of these, they have a domain where x can be greater than or equal to 0. Or you can write that as 0 to infinity. So even though they did not give us an interval, you can kind of find it on our own, at least for problems like this where you know there are undefined values. So from 0 to infinity, and actually this would be an open, I don't know why I put the, from 0 to infinity. Because remember, the critical point is from A to B, but not including A or B. So you can't include infinity, and in this case, you can't include 0. Okay, so we know f prime of x equals 0 when 2 times x to the 3/2 power minus 6x to the 1/2 power equals 0. Okay, so we can rewrite x to the 3/2 power. So we can make that 2 times x to the 1/2 power. Because x to the 2/2 plus 1/2 is 3/2. Minus 6x to the 1/2 power equals 0. So with both of these terms, we can actually factor out a 2 times x to the 1/2 power. Can be factored out. Okay, so if we factor out that 2 and that x to the 1/2 power, that just leaves the x because those two factored out. Minus, so if we factor out a 2 here, that just leaves a 3. We factor out that x to the 1/2, that leaves that one, x minus 3. That's equal to 0. Okay, so now that we've factored it, we can use the zero factor property and just set both of those to 0. So that means 2 times x to the 1/2 power can equal 0, or x minus 3 can equal 0. So the only way 2 times x to the 1/2 power can equal 0 is if x is equal to 0. Or if we add 3 to both sides, we know that x can equal 3. Okay. Now we have the 2 critical points for now, only because we cannot use that 0. Because remember, the domain, so that should be greater than, because it's an open interval from A to B. So in this case, the open interval is from 0 to infinity, which means it can't equal 0. Since x cannot equal 0, and that's only because The interval is from 0 to infinity. X equals 3 is the only critical number. Or critical point. Kind of the same thing. Okay. So the problem like this, you want to be careful. You want to be able to figure out what your domain is. And once you figure out your domain, if one of the critical points happens to fall on the endpoints of the domain, you know you can't use it. This is one of the trickier ones they have. Most of them either fall in or out of the domain. But when they fall right on it, that one gets a little bit tricky. All right. Any questions on that one? All right. Anyone still writing? All right. So let's say, for example, if we wanted to find the absolute minimum and or it could be one, could be the other, could be both. Absolute maximum and just in case, every once in a while, this is also known as the absolute extrema. So if you see a problem that says find the absolute extrema, they just mean the absolute minimum or absolute maximum. Of the function f of x is equal to 3 minus 4x minus 2x squared in the interval from negative infinity to infinity. Okay. Now with this one, you could just use your calculator to graph this and find out if it's concave up or concave down. But we know it's a quadratic equation because it's x squared or a degree 2 polynomial. But if you don't have your calculator, if you notice, if you just rearrange these, so if you have f of x is equal to negative 2x squared minus 4x plus 3. Your leading coefficient is negative. Not equal to, just less than 0. Okay. And just a real reminder that it's in the form ax squared plus bx plus c. So we know when that a is less than 0, then it's concave down. So when a is less than 0, the graph is concave down. Okay. So that rule only applies to quadratic functions. So if it's concave down, we know the graph is going to look something like that. which means that our vertex on that graph is going to be our absolute maximum. Okay, so for this one, we know that we're looking for an absolute maximum. When your f prime of x is equal to 0. Okay, so we know that if f of x is equal to 3 minus 4x minus 2x squared. Actually, I'll write it in the descending order form. That one just looks better. Even though it doesn't matter as far as the answer goes, I just like the way that one looks. So negative 2x squared minus 4x plus 3. So to find our derivative, we do the power rule. So we have negative 2. We bring down this 2. So negative 2 times 2 is negative 4 times x to the power of 2 minus 1, which is just 1. So that's negative 4x. Minus 4 times the derivative of x. Well, derivative of x is 1. So negative 4 times 1 is just negative 4. And the derivative of a constant is 0, so that just disappears. Okay, so we know that f prime of x is equal to 0 when negative 4x minus 4 is equal to 0. So if we add 4 to both sides and divide both sides by negative 4, we know that this is true when x is equal to negative 1. And this is your critical point. Okay. In some textbooks, they will call the critical point where the derivative is equal to 0. They'll call that the stationary point. So it's also known as the stationary point. Now, the point where it's undefined, they refer to that as the critical point, and this is the stationary point, but they both fall under the term critical point. So some textbooks just switch it up. I don't know if Newton changed it or not. But if you happen to see stationary point, then that's all that means. Okay, so now we have to find out, well, we already know that it's the maximum. Let's say if you didn't graph it. To find out whether or not it's the minimum or maximum, we just have to find the second derivative. Remember, that's just the derivative of your first derivative. Which in this case is just the derivative of negative 4x minus 4. Okay, which means that your second derivative, the derivative of negative 4x is just negative 4. And the derivative of negative 4 is 0. So our second derivative is just negative 4. So at the point x equals negative 1, because that's our critical / stationary point, you know, the second derivative at negative 1, well, there are no x's to replace here, so it just stays constant at negative 4. So we know that since the second derivative at our value x is equal to c is less than 0, the graph is concave down. Okay, so there are multiple ways to tell whether it's concave up or concave down. Like I said, if it's quadratic, we know that if your leading coefficient is negative, it's concave down. If this would have been positive 2, we know it would have been concave up. But in case you don't graph it, you can always just figure it out using the second derivative. If your second derivative is negative, concave down. If it would have been positive, it would have been concave up. Okay. So now we just have to find what that maximum value is. Some questions will ask what the maximum value is, some won't. But all you have to do is plug that critical point into your original function. And that will just give you the y value, which is your maximum. Okay, so to find the, I guess you can call that the absolute maximum value, plug x equals -1 into our original f of x function. Not the derivative, but the actual f of x. So that means f of -1 is just equal to -2 times -1 squared minus 4 times -1 plus 3. So -1 squared is just 1. So -2 times 1 is -2. -4 times -1 is +4 plus 3. Okay, so we know f of -1. So if we simplify that, you know, f of -1 is just 7 minus 2, which is 5. Make that a little clearer. There we go. So we know that the point of the absolute maximum is at the point -1, 5. Okay, so again, some questions might just want you to find the x value where the critical point is. So you'll see a little box that says x equals, then it's blank. Then you know this is all they want. But if they say find the point of the critical value, then you're going to get that critical point and plug it into your function and find the y value. So little tweaks in wording kind of tell you what they're looking for, even how they present the answer. All right, any questions on that one? All right. Okay, looks like everyone's done writing. So let's say, for example, we wanted to find the absolute extrema. And remember, that just means your minimum and or maximum. Of f of x is equal to 3 times sine of x times cosine of x over the interval from pi over 4 to pi. Okay, so remember your critical point is where your f prime of x is equal to 0 or it's undefined. Okay, so in this case, it looks like it'll just be an undefined critical point. Not undefined, an f prime of x equals 0 critical point because there are no undefined values. You have the product of two continuous functions, which will be a continuous function. Okay, so we have f of x equals 3 times sine of x times cosine of x. Okay, so we want to find the derivative of the product of two functions. So we know we're going to have to use the product rule. So your f prime of x is equal to, we'll go ahead and factor that 3 out to the front. Your first function times the derivative of your second plus your second function times the derivative of your first function. Okay, so we know that f prime of x will equal 3 times that sine of x just stays sine of x times the derivative of cosine is negative sine. So we have negative sine of x plus cosine of x times the derivative of sine is just cosine. Yeah, I'll put parentheses around that one. Okay, so we know that f prime of x is equal to sine times sine is sine squared. So it's negative sine squared. So 3 times negative sine squared of x plus cosine times cosine is cosine squared. So plus cosine squared of x. And you could distribute the 3, but you don't have to. Only because that whole thing will equal 0 whenever negative sine squared plus cosine squared is equal to 0. That 3 is just going to be divided out anyway. So f prime of x equals 0 when negative sine squared of x plus cosine squared of x is equal to 0. Uh-oh, didn't even realize it was turning. And make that squared a little bit neater. So if we add sine squared to both sides, we just get sine squared equals cosine squared. Or you can say cosine squared equals sine squared. Same thing. So if we square root both sides, so we take the square root of this side and square root of this side. Remember, when using the square root property, you have to have your plus or minus. So we square root sine squared, that's just sine of x, is equal to plus or minus the square root of cosine squared is just cosine. And it doesn't matter which side you put the plus or minus on. Now, this is only true when x is equal to pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4. You kind of see the pattern here. And keeps on going. So we can see here that our interval is from pi over 4 to pi. Okay, so we're going to use 3 pi over 4, well, pi over 4 to 3 pi over 4, plus we're going to go a little bit further. So this is only true in this interval, so this is where we're kind of going to hang around. So we know x equals pi over 4 and x equals 3 pi over 4 are the only one of those values that's actually in the domain or in our interval. So the only values in the interval. Okay, so if we didn't have that interval, we literally could go on like that forever. And I'll put the interval right next to it. Pi over 4 to 3 pi, to pi. There we go. Okay, so since we're going to test pi over 4 and 3 pi over 4, we know everything in between works, but we also want to test the endpoints just to see. All right, anyone still writing? Okay. Okay, so let's test f of 3 pi over 4. Well, that's 3 times sine of 3 pi over 4 times cosine of 3 pi over 4. Well, that's 3 times sine of 3 pi over 4 is square root of 2 over 2. And cosine of 3 pi over 4 is negative square root of 2 over 2. I'll put it underneath it just to make it a little neater. Okay, so square root of 2 times square root of 2 is 2. So if we multiply these two, it cancels out with one of the 2's down here. So these two will cancel out with one of the 2's down here. So we're left with just -3/2. Now if we plug in our f of pi over 4, that's equal to 3 times sine of pi over 4 times cosine of pi over 4. Oops. Okay, well, sine of pi over 4, square root of 2 over 2. So that's 3 times square root of 2 over 2. And cosine of pi over 4 is also square root of 2 over 2. And that gives us positive 3 over 2. Okay, so we tested our critical points. Now we have to test the endpoints for pi over 4 to pi, just to see if any of those values are higher than the negative 3 over 2, 3 over 2. Okay, so this one, we already did it. We did it right here. So we just have to do that one. Bring that arrow down a little bit, give us a little more room to work with. So f of pi is equal to 3 times sine of pi times cosine of pi. We know sine of pi is 0, so that's just 3 times 0 times cosine of pi is -1, which is just 0. Okay, so we can look at all of our values here. We know that at the critical points, our absolute maximum, bring that up a little bit, is 3 over 2. And that's at x is equal to pi over 4. And our absolute minimum is -3 over 2. At x is equal to 3 pi over 4. All right, any questions on that one? All right. So now we're going to start on section 4.4. Which is the mean value theorem. before we look at the mean value theorem, we have to look at what is called Rolle's theorem. Okay. So what if we let some function that we will call f of x be continuous on a closed interval from x equals a to x equals b, and differentiable on the open interval from x equals a to x equals b, which means the derivative exists everywhere in between there, but possibly not at a and b, a or b. Okay. So let's say there's a point where f of a is equal to f of b. Now, if that's the case, then we know there's at least could be more than, but at least one point, one value that we will call c, that's actually in the interval, where f prime of c is equal to 0. Okay, now visually, all this means that, let's say if we have our x and y axis, I'll make that a little longer. Let's say from x equals a to x equals b, we have a continuous function. We'll just draw a random continuous function. Again, we're only looking at x equals a to x equals b. Okay, so we can see that it's continuous. And if we look for the derivative at any of those spots, we'll see the derivative exists. We take the limit from the left and right at any point, we'll get the same thing. Okay. So let's say we know that there's a point here where if you plug in a, you'll get f of a. And if you plug in b, you'll get the same value, f of b. Okay, so they're equal to each other. Okay, so that means somewhere along the line, this graph had to turn around in order for those two values to meet, which means if it turned around, then there exists some point between A and B, and that point we will call point C, where your f prime of C is equal to 0, or your slope of the tangent line is equal to 0. Oh, wrong. I'll put that over here. Excuse me. So let's say, for example, if we want to find the value of C that is in the interval from -9 to -1, guaranteed by Rolle's theorem, for g of x is equal to -2x squared minus 20x minus 15. Okay, so if you notice, the first thing we had is f of a is equal to f of b. So what we have to do, we have to see if g of a is equal to g of b, because that's one of the conditions. Okay, I want to see if g of a is equal to g of b. Or in this case, that means that g of -9 is equal to g of -1. Okay, so g of -9, that's just -2 times -9 squared minus 20 times -9 minus 15. Okay, and I just plugged all of that into the calculator because I didn't feel like doing it by hand, but g of -9 is equal to 3. Okay, so now g of -1, that's just -2 times -1 squared minus 20 times -1 minus 15. And again, plug it into my calculator, and we know that g of -1 is also equal to 3. So that condition is met. Okay. So we know it's continuous because all polynomials are continuous. And we know it's differentiable because if we take the derivative of this and plug in any value between -9 and -1, we'd get a real number. So we know it's continuous and differentiable. So all the conditions are met. Okay. So we know that g of x is continuous and differentiable. Also, g of a is equal to g of b. Then we know that a g prime of c equals 0 exists. Okay, so that's all that told us. We now just have to find that value of c. Now, if we plugged in g of -9 and got 3, and then g of -1 and got 4, then we'd stop right there because the conditions aren't met, so we don't even have to bother going any further. But because they are equal, we can keep going. Okay, so we know that g of c is equal to -2 times c squared minus 20 times c minus 15. just replacing the x with c. And g prime of c is just the derivative. So that's -2 times the derivative of c squared, which is 2c, minus 20 times the derivative of c, which is 1, minus 15. Well, the derivative of 15 is 0, so that just becomes, you can say minus 0 if you want, or you can just leave it blank. So we know that g prime of c is equal to -4 times c minus 20. Oh, should have put 1 there. I don't know why I put c. There we go. The derivative of c is 1. Okay. So we know that our g prime of c is equal to 0 when -4c minus 20 is equal to 0. So if we add 20 to both sides, we have -4c, those two cancel each other out, is equal to 20. So if we divide both sides by -4, those two cancel each other out. So we have c is equal to 5 divided by -5. 20 divided by -4 is -5. So that's the value that's between -9 and -1 that proves that Rolle's theorem does apply to this problem. All right, any questions on that one? All right. Oops. Let's see, looks like I'm running out of paper. Let me grab some more just in case. Put that right there for now. Thought I had enough. There we go. All right. So now let's look at the mean value theorem. Okay. Now the mean value theorem starts off with the same criteria as Rolle's theorem. And that's just saying, what if we let f of x be a continuous function on the closed interval from a to b and differentiable on the open interval from a to b. So they both start off the same. Okay. And they both have some number c in the interval from a to b. And we know that then there exists a value C that's in the interval from A to B. Okay. Now this one kind of goes a little bit of a different direction. Okay, such that f prime of C is equal to f of B minus f of A all over B minus A. Now we have our definition, but all of that means visually is, let's say if we have our X and Y axis, and we have some random continuous function. And like I said, we'll draw just a nice easy function there. And that's from x equals A, so we'll put A about right there, to x equals B. And we'll put B about right there. Now this one, f of A doesn't have to equal f of B. It can, but it doesn't have to. Okay, so if we plugged in A into our function, well, we get some value f of A. And if we plugged in B into our function, we'd get some value f of B. So this point right here, this is the point B, f of B. And this point right here, this is the point A, f of A. And if we grabbed a straight edge and connected those two lines, and try to get as close as possible, there we go. So if you remember, we actually did cover this a while back, where if you have 2 points on a nonlinear graph, you just draw a line through those. That's the slope of your secant line. Let me make that a little shorter so I have room to write. That's the slope of the secant line. And remember, that's still y2 minus y1, or in this case, f of b minus f of a, all over your b minus a. Okay. So what this theorem says that if you have that slope of the secant line, which is the right side here, f of b minus f of a, all over b minus a, then somewhere in between there, as long as it's continuous and differentiable everywhere between there, there exists some point that has the slope in the exact same direction. So we'll call that point point C. And if we draw our slope at that point, that's our f prime of C. So that means f prime of C and your slope of the secant line have the exact same value. Oops. All right, any questions on that one? All right. So let's say, for example, if we wanted to find the value, and we'll call that value C, in the interval from x equals 7 to x equals 9, guaranteed by and of course, the mean value theorem. A lot of times you'll just see MVT. You get tired of writing out the whole thing over and over. Guaranteed by the mean value theorem for f of x is equal to -7 times x minus 9 squared. Okay, so for this one, remember the goal for this one, whenever you see a mean value theorem problem, you want to find where f prime of c is equal to the slope of the secant line, which is the same as saying you want where f prime of c is equal to f of b minus f of a all over b minus a. Okay. And you can start with either side. I always just start with f prime of c. So first, we want to find f prime of c. So f of c, we're just going to replace x with c. So it's -7 times c minus 9 squared. Well, we know f prime of c, we just factor out that -7 and find the derivative of c minus 9 squared. So using the chain rule, we're going to bring down the 2. So 2 times c minus 9 to the power of 2 minus 1 times the derivative of what's inside. Uh-oh, my sleeve keeps getting caught up in the paper. Times the derivative with respect to c of c minus 9. Which in this case, this derivative is just 1. So no point in writing out an entire step just to put times 1. Okay. So if we go ahead and multiply those two, we know that f prime of c is equal to -7 times 2 is -14 times c minus 9 to the power of 2 minus 1, which is just to the first power, times c minus 9. Okay, so we have our f prime of c. Okay, now we want to find our slope of the secant line. Okay. Well, we know the slope of the secant line is f of b minus f of a all over b minus a. Okay, well, we know that our interval is from 7 to 9. So this is our A, and this is our B. Which means what we're looking for is f of 9 minus f of 7 divided by 9 minus 7. Okay, so right here on the side, we can go ahead and find those two really quick. Okay, so we know that f of x is equal to negative 7 times x minus 9 squared. So we know that f of 9 is equal to negative 7 times 9 minus 9 squared. Well, 9 minus 9 is 0, so 0 times anything is 0, so that all just becomes 0. So we know that f of 9 is equal to 0. And we do the same thing for f of 7. F of 7 is just equal to negative 7 times 7 minus 9 squared. Okay. So if we simplify that, we know that f of 7 is equal to negative 7. 7 minus 9 is negative 2. That gives us negative 2 squared. So f of 7 is equal to negative 2 squared is positive 4. Negative 7 times positive 4 is negative 28. So we have our f of 9 and f of 7. And point a little arrow to that one. So that means our slope of the secant line is equal to f of 9, which is 0. That's just 0 minus f of 7, which is negative 28, divided by 9 minus 7, which is 2. So that gives us 28 divided by 2, which is 14. So we know the slope of the secant line is equal to 14. Okay. So now the last step is to set these two equal to each other and solve for c. So we're going to set f prime of c is equal to the slope of the secant line and solve. Okay, so f prime of c is negative 14 times c minus 9. So we have negative 14 times c minus 9 is equal to the slope of the secant line, which is 14. So if we divide both sides by negative 14, I'll just rewrite that. So negative 14 times c minus 9 divided by negative 14 equals 14 divided by negative 14, where those two cancel out. And we have c minus 9 is equal to negative 1. So if we add 9 to both sides, those two cancel each other out. So we know that c is equal to negative 1 plus 9, which is 8. So that's the value guaranteed by the mean value theorem. where if we graph the slope of the secant line and we graph f prime of c, we would have the exact same slope value. All right, any questions on that one? Okay. So again, with this one, all you have to do is solve one side, solve the other, make them equal, you're set. Then solve from that one. All right, anyone still writing? Okay. Okay, so for section 4.5, we're going to look at how the derivative can help make the shape of a graph. The derivative and the shape of a graph. So we already kind of looked at concavity, but now we're going to actually define it using derivatives. Okay. So let's say if we let some function that we would call f. Again, it could be f of x, f of t, f of r. We just know it's a function f. And we know it's differentiable on an open interval from a to b. Okay. Now, if those conditions are met, one of two things can happen. We know that if the graph is concave up, then we know that the graph lies above all of its tangent lines. In that specific interval. Okay, so what that means is that, let's say you take some concave up function. So we have our function, and we know it's concave up. So it looks something like that. And where's my ruler / paper? Now I'll just get an index card. Here. So let's say we decide, okay, we're going to draw our slope of the tangent line, or first derivative at this point. So the first derivative will look something like this, give or take. Well, what if we decide to draw one at a different spot? So if we drew one right here, same thing, it'll look somewhat like that. And if we drew one here, same thing, it'll look like that. So no matter where you draw your tangent lines, it'll always be below your graph, or your graph will always be above your tangent lines. Okay. And the second possibility, I'll just write the 2. If the graph is concave down, then it's kind of the opposite. The graph will lie below all of the tangent lines. In the interval from A to B. Kind of separate those two a little bit. There we go. Okay, now for this one, all that means that if you have a concave down graph of a function, so concave down, so it'll look somewhat like that, give or take. So let's say if we wanted to plot the slope of the tangent line here. Well, if we wanted to plot it there, again, it would look kind of, sort of, somewhat like that. Or if we wanted to plot it here, it would kind of, sort of, somewhat look like this. Or if we wanted to plot our tangent line here, it'll look a little like this. Okay. But the one thing they all have in common is that all of the tangent lines are above the graph, or the graph is below all the tangent lines. Oops, straighten that up. Okay, which brings us to the actual definition of concavity. We have the idea of concavity, but this brings us to the genuine definition of it. So the definition of concavity. Okay, so what if we let f be a differentiable function on the interval from a to b? And the graph is concave up on that interval if f prime of x is increasing. And concave down if f prime of x is decreasing. On the interval from a to b. So this was kind of the idea I was trying to give across with the paperclip earlier. Okay, let's say if you have a concave up. That could have looked a little bit better than that. Try to make it somewhat even. That's good enough. Okay, so we have a concave up function. Okay, so again, let's say if you draw the tangent line here, and it looks like that. So let's say in that case, the slope is -2. The slope of the tangent line is -2. As you go to the right, that slope is going to increase to where now at this point it could be -1. It's not as steep. And at some point, you're going to have a tangent line with a slope of 0. Then eventually maybe a slope of 1. Then maybe a slope of +2, and so forth and so on. So we can see it went from a possible -2 slope, and it was slowly increasing to where it's positive. So the tangent line was slowly increasing. Whereas if you get the concave down graph, and we'll make that one concave down. If you start on this side, the slope of your tangent line could be something like +2. Then as you move over to the right, you see here it could go down to something like +1. Then eventually right here at your vertex, it would be 0. Then you would have, I'll just draw a little small one there since I don't have a whole lot of room. Then eventually it would start being negative. Okay. So you can see as you slowly go to the right, the slope of the tangent line goes from being kind of steep to not as steep to 0, then eventually negative. So your f prime of x is decreasing on that interval. Right. So from that idea, that brings us to what is called the first derivative test. Okay. So we know that when your derivative, f prime of x, changes from positive to negative, then we know that your f prime of c that equals 0 is a local maximum. And sometimes the local maximum is called the relative maximum. They may call it one or the other, or both. They may switch it up per problem. Okay, so again, all that means is that you have some random graph. We know on this side, your f prime of x is greater than 0. It's positive. Then it eventually hit on this side, where we know the slope is negative, so your f prime of x is negative. So if it goes from positive to negative, then this point right here, where your f prime of c is equal to 0, where your slope of the tangent line is 0, that point is your maximum. Now, when the opposite happens, when your derivative changes from negative to positive, then we know the point where your f prime of c is equal to 0 is a local minimum. Is a local or relative minimum. Okay, so once again, just to kind of help visualize it, let's say if you have your function f of x, and we know we get the tangent line on this side, this is decreasing, so we know that the slope of the tangent line is negative. Whereas if we get a point on this side, it's increasing, so we know that the slope of the tangent line is positive. That means that the point where f prime of c, and I forgot to put my c up here, so this should be above some value c. The point where f prime of c equals 0, that's our local minimum. Or relative minimum, depending on which term the problem wants to use. All right, so we're gonna stop there only because these problems get a little bit lengthy. So I'm not 100% positive we'll finish it in 15 minutes, but we will start here on the example on Monday. Let's see. Is 4.5 on Monday. All right, you too.